This is lesson 3 on antennas. We're in part 3 of TTC Technologies. Part 3 is wireless communications. We previously talked about some of the basics of radio frequency wireless communications. And in the last video, we described modulation. So in this video, we're going to talk about the use of antenna as part of a wireless communication system. And one way of thinking about an antenna is that it is a transducer. And a transducer is a term that came up when we were talking about sensing systems back in command and data handling portion of the course. But its root meaning, the term transducer, is something that converts from one form of energy to another. And an antenna does exactly that. An antenna converts a voltage and current in a conductor to a time-varying electromagnetic wave that travels through air or space, and it can also go the other direction. It can take a time-varying electromagnetic wave that interacts with it, with the antenna, and can convert that to a time-varying voltage and therefore current flowing in the conductor portion of the antenna. And the nice thing about this is when that conversion takes place, it converts the signal from one form to another, but the signal has the same frequency content, so the time-varying aspect of the signal is preserved, and it's that time-varying aspect that holds our information. So transmission goes from the voltage and associated current in the antenna to a radiated electromagnetic wave, and reception is the opposite. The wave hits the antenna, induces the voltage, and causes the current to flow in the antenna, and that is our receive process. We think in an ideal sense about a purely omnidirectional antenna, something we call an isotropic antenna. It will take whatever power is invested in the transmission, and it will spread it equally in all directions, send it equally in all directions. And in a sense, it's as if the energy per unit time is spread out over a sphere that radiates from the antenna. And as it radiates, it increases in size, or the distance between the potential location to receive and the transmit point itself grows. And as it does that, it spreads its energy out over a larger and larger surface area, because as that shell increases in radius, it increases in surface area. And because the same amount of energy is being spread out over a larger and larger area, the power per unit area on that shell will decrease. And it decreases like an inverse square law. And you can see the inverse square law there at the bottom of the slide. And so that's the power transmitted is essentially spread out over the surface area of the sphere, and that goes as an r squared there in the denominator. You can imagine placing an antenna some distance away from the transmitter. The antenna will have a certain area, certain aperture size, and that effective area is what receives the radio wave at that location. And so if I have a certain amount of power per unit area that's being broadcast and spread out over the surface of that sphere, at the distance between the transmitter and the receiver, at that radius of the sphere, we take that particular power per unit area and multiply it by the effective area of the antenna to determine how much power is received by the receive antenna. Now, the isotropic antenna broadcasts equally in all directions. It's, in the truest sense, an omnidirectional antenna. But most antenna, in fact, most antenna of interest, have some directionality associated with them. And that directionality is an effective gain of the signal strength, as if we were broadcasting with more power in the direction of the antenna. And conversely, It's as if we were broadcasting with less power in other directions. So this ability of an antenna to focus the electromagnetic energy in a particular direction is very useful to us, since we can sort of use the mechanical design of the antenna rather than more electrical power. So this ratio of increased effective power is called the gain. And we like antennas typically with large gain, although there are some drawbacks associated with that, which we'll talk about. So you can see here in the diagram, the antenna is focused to the right, and we have a nice large gain as indicated by this diagram that we use. And this is called a beam pattern diagram. And it shows you the effective gain of the broadcast signal given the characteristics of the antenna. And you can see a nice big lobe pointing out there. The lobe has a large size to it, which implies a large gain. And you can see in the other angular directions, we have a lot of attenuation. We have very little of the beam pattern being drawn in those other directions. And that's attenuation. That is an equivalent loss in those directions. You'll see on the bottom diagram some weird looking things that come off the side of this main lobe. And these are called side lobes, and these are non-ideal focusing of the beam at to a lesser extent than the main lobe. But it's for real antenna in a practical sense. It's not like we have the main lobe and very little or zero power invested in all other directions. The power does taper off in other directions, but sometimes you have little focus concentration areas called side lobes, which you need to pay attention to because you are broadcasting with some level of energy in those specific directions. And so that might be an interference source to somebody else, and you think you're pointing one direction and somebody in a different direction is hearing your broadcast because they're basically captured in a side lobe. What this slide shows is a closer look of the antenna pattern for a particular antenna. This is roughly an omnidirectional antenna. It is slightly directional. This is called a dipole antenna. And it's a strand of wire or a conductor, a straight piece. And you can see to the right a three-dimensional representation of how the energy radiates from this wire. And then at the bottom, you see different cutaway planes of the beam pattern. And this effectively looks like a sort of donut. So along the axis of the wire, you have some attenuation, but everywhere else you have pretty strong broadcast. And because you have good signal going to most of the region, the equivalent gain is fairly low. But the point of the diagram is to show how you would have the conversation about the beam pattern, the gain of a particular antenna, and how it is physically oriented with respect to the mechanical installation of the antenna. So a couple terms, we often talk about the main lobe, which we've mentioned in the previous slide, and the idea of side lobes. With the main lobe, we are interested in sort of the width of that main lobe, and we call that the beam width. And what we do is we take the peak power level coming out of the main lobe, and we look to either side of it to see where it drops off by 3 decibels. And we peg those points, and the angular distance between those points is what we consider to be the beam width of the antenna. So the beam width spans the two -3 decibel points from the peak power of the antenna. And for this example, we have a very low gain because it really is spreading energy out fairly equally in all directions with the exception of the axis. So the gain is only 2.2 decibels and the beam width is very broad. It's about 80 degrees. Now I'm using this term decibels, and it's the first time I use it in the course. Some of you may already be familiar with it, but what we're really talking about is sort of this ratio of power, and we're talking about peak power and the power at any given angle, and we're comparing it to this abstract notion of the isotropic power, kind of that perfect sphere that you saw earlier. And we're really looking at the ratio of that. If our antenna really truly is omnidirectional, then it's isotropic, and so the ratio of power in any direction compared to the ideal isotropic um, power would be 1, and we would have 0 decibels in terms of gain. Decibels itself is a logarithmic unit, and it allows you to logarithmically compare two quantities, and that's what we're doing. We're comparing the power out of our real antenna at a given angle and comparing it to the equivalent power that you would get out of this abstract notion of the isotropic or purely omnidirectional antenna. So the isotropic antenna is our reference in this sense. In order to establish a comparison, and a logarithmic unit of that comparison is the decibel. So the number of decibels in terms of the actual equation is 10 times the log base 10 of the power ratio itself, and that power ratio is the power to isotropic power. We certainly talk about peak power for the gain, but you can imagine the number of decibels sort of at any angular position with respect to the mechanical installation of the antenna. So, for example, just to walk through the math, if we were talking about an antenna with a gain of 15 decibels, we would plug 15 into that equation, and the way to sort of invert the log 10 function is to take both sides of the equation. You take 10 to the power of what you see there. So we take 10 to the power of 15, and we take 10 to the power of 10 log 10 of the power ratio. Before you do that, it's actually a little simpler to divide out both sides by 10, as you see here in the slide. So you wind up with peak power equaling 10 to the 1.5 power times isotropic power. And when you work through the math, you see that the 15 decibels is equivalent to a ratio of 31.6. And so we're saying that the peak power to isotropic power ratio is 31 times. So peak power is 31 times that of the isotropic power. So that's a pretty significant gain in that one direction. And we would imagine with that much gain that most likely for that antenna we would have a lot of attenuation in the other directions. So when we look at that peak power, we then look both sides to minus 3 decibels. So if we had a 31 decibel peak power in the direction we're pointing the antenna, we would look on either side to where we hit about 28 or 28.6 dB. That would be the 3 dB drop-off point on either side of the peak power point, and we would look at that angular distance, and that would be the beam width of this particular antenna. So if you walk through the math, 3 decibels is approximately a factor of 2, and minus 3 decibels is a factor of 1/2. And as a rough approximation, you can take, for every 3 decibels you go in terms of increasing or decreasing, in terms of gain or attenuation, you can imagine a factor of 2 being involved. So if I have a gain of 3 decibels, that means that my peak power is twice as much as the isotropic power that I would have expected from that antenna. And if it's minus 3 dB in a certain direction, then I've lost half of it. So the same would go with 6 dB or 9 dB. So if I had 6 dB, then I have 1/4 of the power, because I lose a half with the first dB, and I lose another half with the next 3 dB. So a 6 dB gain would be 4 times the power, and a 6 dB loss would be 1/4 of the power. The reason we use decibels and the logarithmic expression is when you do that, it turns ratios and factors that are being multiplied and divided into quantities that are being added and subtracted. And so it changes the algebraic form of the expression, and sometimes you want to go back and forth depending upon the ease of the math. And we're going to see that when we get to the link equation, because we'll be dealing with decibels in the link equation, so we can add and subtract terms. So back to antenna. So the next few slides kind of walk through a couple different typical physical realizations of antenna and just to do some rough comparisons. And this is very generic. It all depends upon the exact parameters of the antenna, its size, and frequency being used, and everything else. But just to give you a feel for the different kinds of antenna that you typically see and that we certainly see in operating spacecraft, and certainly those here at Santa Clara, are the ones on the next few slides. So we do see this sort of what we call a whip antenna, but the dipole or roughly omnidirectional antenna that we saw in the example slide before. That's the kind of thing that you would see off a handheld antenna. Sometimes we have these up on the roof um, for other communication links, and so you can see that that largely it looks very close to an isotropic beam pattern, with the exception of we have some losses there along the axis. So really what's happening is the majority of the energy is coming out radially uh, from the mast of the antenna. If I want to do a good job of transmitting in a certain direction, I don't want to point the antenna in that direction, down axially, because that's actually the direction of most loss. So we get this kind of very broad donut pattern. We get very low gains, only 1 to 3 dB, because most of the energy is really spread out nicely, so it doesn't result in a pronounced peak of gain. And because it's spread out so much, we get very wide beam widths, 80 degrees, 90 degrees typical, sometimes even higher. And we often see these antennae being used in the VHF and UHF frequencies. And for us, that means we use this a lot for the ham radio links on board the spacecraft. On the right, you see something known as a patch antenna, and this tends to have a slightly higher gain. So you see kind of it's still very broad, but a big lobe coming out there in the beam pattern. Um, and so we have more of a gain. So this is typically the ones we use, more like 5 or 10 decibels, slightly narrower beam width than the omnidirectional antenna. So now we're looking more like maybe 60 degrees or so. And these are often used in the 900 megahertz or the 2.4 gigahertz range. And that's how we use it, in the 2.4 gigahertz range on board the spacecraft. A couple other kinds of antenna on the left. We have something called a Yagi antenna. This is like the old television aerials when we had wireless reception, for those of you who may or may not remember that. And you can see the beam pattern down below. And now we're looking at more pronounced gain, a tighter beam width, more directionality. Depending upon the number of elements and the length, anything from a handheld 5 or 7 element kind of thing that might be a meter in length to something that's more like 5 meters in length, like the sort of things we have on the roof. The gain can range anywhere from between 6 to 20 decibels. And now we have tighter beam widths, so more like 30 or 40 degrees. And we still use these largely in the VHF and UHF bands. And again, for us, that means we use these primarily for our ham radio links. Then on the right, you see a dish antenna. So this is the notion of a parabolic reflector. These tend to give much tighter beams, depending upon the size of the reflector, anywhere from 20 to 45 decibels in gain. Beam widths are often less than 10 degrees, and we use these at much higher frequencies. S-band for us, C-band higher than that. And down in the beam pattern, you can see a real tight focus of energy for this kind of antenna. So here's some of the antenna we see for the work we do with satellite operations at Santa Clara. You can see on board the spacecraft. That's a little patch antenna there on the left end of the spacecraft. We sort of have that main structure, and then what looks like sort of a tuna can cylinder sticking on the end of it, and then on the very end of the tuna can is a patch antenna. And just above that, maybe a little hard to see, but just above that, sort of protruding from the satellite out to the left, is basically a whip antenna. So that's acting as a dipole, roughly omnidirectional antenna, and that's what we use for the beacon broadcast. The patch antenna is what we use for the S-band main command and control link for these spacecraft. In the upper right, you can see the 3-meter parabolic dishes that are on the roof of the main Santa Clara building. We have some at other locations as well. Those are used for S-band two-way communications with these spacecraft. Down on the left, you see what looks like sort of an H configuration. Those are long Yagi antennas that are oriented up and down, and they're both supported in the middle by a cross brace, so they both run off the same position control motors. But those are anywhere from 15 to 20 feet in length, and so they have pretty high gains on the order of roughly 15 decibels or so. And one of those is used at UHF, and the other is used at VHF frequencies. In the middle and the bottom is one of our beacon antennas. So this is not articulating; it just is a static antenna pointing straight up. But it's basically a 5 or 7 element Yagi that we put on these PVC bases, and it's pointing straight up. And when the satellite flies over um, directly overhead, we can get the beacon signals with that. It's enough gain that allows us to do that. On the bottom right, you see our mobile mission control center, and the big feature there in the upper right-hand portion of that photo is a 2.4-meter parabolic dish. That particular trailer, at some point in the near future, will also have some directional Yagi antennas as well. So a real example here, this is the 18-meter SRI dish that we refurbished as part of the GeneSat 1 operation, used it a little bit for Pharmasat. Haven't used it lately because of we now have our own 3-meter dishes, but this is an 18-meter diameter dish, and off to the right you can see the beam patterns. You can see it sort of in two different cutaway planes, and for the purposes of our discussion, we can look at either one. I'll look at the top one. But this is a 45 dB gain antenna, so very, very large antenna, very high gain, very directional. And if you look at that beam pattern, now this is sort of spread out in a Cartesian plot as opposed to a polar plot, but you can see how tight this pattern is. So at the 0 relative dB point, that's uh, the peak power coming out of this in a directional sense, and that's really overall compared to the isotropic standard 45 dB. But you can see how this drops off, and you can see that within 1 degree, we're many dB down from the peak. And remember, 3 dB is one half of a drop. 6 dB is 1/4. So you can see how dramatically this drops off. And that ties into sort of the negative effects that I want to talk about in terms of gain. It's wonderful to have a very high gain antenna. It really focuses your power. For the same power, you can broadcast over more range, or at the same range, you can have a successful link for less power. So those are both really two really excellent ways of exploiting the idea of high gain. But the higher the gain, the more the directionality. And what that really means in a practical sense is you have to be very good at pointing your antenna. And this can actually become a challenge for everybody says, oh, I would love to have an enormous antenna. Think of the gain I could get out of it. But you would really have to have an excellent pointing system in order to do that. Otherwise, a little bit of pointing error translates into huge attenuation, and you completely lose the value of the gain. You can imagine sort of this idea of what I often say is you're precisely pointing in precisely the wrong direction, and that does you absolutely no good. You'd be better off with an omnidirectional antenna, quite frankly. So keep that in mind with the antenna that we're talking about. We often are looking for gains, but gain implies directionality, and that implies that you have some sense of where you should be pointing and that you can actually achieve that with your control system. A few slides just on some general thoughts in using and installing antennas. They should be pointed at each other. They should be within line of sight. That's the main mode of propagation. They should be clear of obstacles. If there's obstacles in the way, that's going to cause distortions and absorption. Is a big area of absorption. Other objects that are sort of harder, like buildings and signs and things like that, will cause multipath and reflections. You can see in the second level, correct versus incorrect. On the left, correct. On the right, incorrect. And one reason is that it's rotated. The two Yagi antennae there are rotated by 90 degrees, and so the polarity of those waves are going to be different, and you're going to suffer a loss as a result. You can see in sort of the third layer down on the right, there's an example of the antennas being installed backwards. So you're broadcasting in the incorrect direction, and so on and so forth. So just some tips on orientation and directionality and things like that when you're using antenna. In terms of the physical installation itself with the wiring, sort of a couple of rules of the road. You want to limit the length of your cable because the longer the cable, the more the loss in the cable. You don't want to create a coil because that's going to create a magnetic field, a time varying magnetic field that will interact with and distort what you receive and what you transmit from your antenna. Water in antenna lines is a big issue, and so just physically allowing water to drip off and not run into your connectors and things like that is something that we have to worry about, because if water gets into your antenna line or into your connectors, which it will, um, you can easily lose a few dB of power because of that. A couple other practical considerations. We've sort of been looking at the antenna patterns in a very idealized sense, as if these antennae were out in free space. In reality, I'm mounting it to something, and that something, the material, the physicality, the geometry, that plays into the characteristics of the antenna. At the very least, it might be a source of reflection and noise. It might distort or bend the idealized beam pattern. So you can see here is an example of a um, different set of beam patterns for what really is largely a dipole antenna. And it's a little hard to see, but the dotted pattern there, the fine resolution dotted pattern, is kind of a typical donut shaped cutaway of a monopole. But then if I have this on the ground, right above the ground, or um, right above the surface where I have salt water, you can see I have massive reflections and a complete distortion in both cases, with the two additional curves that are on there. So that's a very significant difference in the beam pattern. So you really need to be aware of the surroundings when you mount an antenna. What's it attached to? What's immediately behind it? Um, is it something that is going to maybe improve or detract from the characteristics of the antenna in terms of its gain? Will it alter the beam pattern? If so, how? And so for those of you familiar with the installation on the roof, we have concerns about the fact that we have big HVAC units up there, and those are big metallic reflective kinds of surfaces, and how does that affect our beam patterns? That's a concern that we have for our own installation. It's also interesting to note that the people who do very sophisticated antenna design, folks at Loral, Lockheed, and aerospace companies that are making production level communication satellites, do some really fantastic things with how they shape the beams when they interact with the Earth for a ComSat, and how you can distort kind of, imagine a nice, pure, idealized parabolic antenna, and if you contort it in various ways, you can change the beam pattern. And effectively, if you have a geosynchronous communication satellite, and you know it's always going to be above a certain portion of the Earth, you don't want to waste energy by broadcasting out into the middle of the ocean. And so, how would you tweak the shape of the parabolic antenna in order to sort of wrap the projection of the antenna around the continents? So that's a pretty interesting uh, challenge, and that can be done mechanically by physically changing the shape of the antenna. It can also be done electronically through phased array systems and through what's known as electronic beam steering systems. Very advanced technology, very interesting. So a couple of the general considerations. Remember that higher gain means a tighter beam width, and that means more extreme pointing requirements. We have different antenna geometries, and they're appropriate for different uses. The geometries imply different gains and beam widths, and they're appropriate for different frequencies. Um, the antenna pointing challenge itself is something we'll talk about in the satellite tracking portion of the course. And then in any wireless system, there are a lot of practical challenges. Certainly those that tie into the antenna would be nearby objects, reflectivity of those objects in the ground or the surface in general, losses with cable, mechanical alignment, the wind blowing and knocking you out of alignment, installation issues, and so on. So to summarize, antenna is a transducer, converts between electromagnetic waves and voltage and current in the antenna itself. The antenna can be used to focus energy. We have this notion of gain, the focusing of energy in a particular direction. So we get increase in effective power in a certain direction and typically a decrease in the other directions. If we have directional antenna, then we have this notion of it's directional in a particular direction. So now we have to worry about pointing the antenna in the direction that we want it in order to exploit the benefits of that gain. And different antennae are used for more or less gain depending upon the frequencies that are being used. So that concludes the antenna portion